So what did we discuss so far? Where did we come till up to? We have started working on what? Designing ANN models. What does ANN stands for? Artificial neural networks. So in deep learning, we have started with neural networks, where we have started working on developing ANN models. So far, how many ANN models did we develop? How many ANN models did we develop? 2. What were they? ANN models for regression task, ANN model for classification task. What is the difference between regression and classification? If the output variable has continuous values, we go for regression algorithm. If the output variable has categorical values, we go for classification. What was the data set that we have worked for regression model? Insurance data set, where the target variable was expenses, where we had continuous values. That is the reason we have designed ANN model for regression, for insurance data set. What was the data set that we have worked when we were discussing about classification? Churn modeling data set, where we have the column called what? Exited. Okay. So we were working on churn modeling, where we have exited column which has zeros and ones, hence we have gone for classification. Right? Now when we talk about building ANN model, we were discussing 3 important steps. What were they? Forward propagation, loss calculation, backward propagation. What is this loss calculation? The difference between actual value and predicted value, which will actually give us the performance of the model. See, our ultimate aim in designing a model is to make it perform well. Okay, if the model is not performing well, or if it is not giving the desired results, we go for the next step, which is backward propagation. Okay, now the ultimate aim of my model is to yield better results, for which I have to get very less loss function. So if I don't get loss function, I go for other alternative, which is back propagation, where I update my weights and biases such that my loss function would be reduced. So I say the heart of the entire model, or the heart of the entire process, lies in back propagation. Do you all agree? Yes or no? I want to design a model which will give good accuracy with very less loss function. And for getting this very less loss function, I have to go for updating weights and biases in such a way that I reduce my loss function. And for updating these weights and biases, we use what? Optimization algorithms. So what was the optimization algorithm that we were working on in the previous 2 sessions? Gradient descent. Yes or no? So gradient descent was the algorithm that we were working, where we try to change or update what? Weights and biases such that my loss function would be reduced, and if the loss function is reduced, my model will work better. Okay. So we have so many different types of optimization algorithms. Okay. The basic or standard optimization, or the general optimization that we start with, is gradient descent, which we have already seen. So what did we see in gradient descent? We update weights and biases by calculating the derivative of loss function with respect to weights from output side to input side. Right? We have seen 5 points. Calculating the loss function of dz2, dw2, db2, dz1, dw1 and db1. These were the 5 points in which we have processed our gradient descent algorithm. Okay. Now today in this session, I would like to explain more about other different optimization algorithms, and how does these optimization algorithms will actually affect the performance of the given ANN model. Are you all clear with this? Yes or no? So understand that the performance of the model depends upon the optimization algorithm that we choose. Okay. So one basic algorithm, optimization algorithm that we have already discussed was gradient descent. We'll study gradient descent types. We have different types of gradient descent. We'll discuss about the types of gradient descent and what are the other alternate optimizers that we have for reducing the loss function. Okay. Once I am done with explaining you about the optimizers, we will switch on to the exercise. Okay. Where we will use Adam optimizer, the new optimizer, instead of what? Gradient descent, and see how the model performance is gradually changed. Are you all okay with me? Okay, we will use the same insurance data set. We will use the same regression model. But what is the change that we are doing today in the session? We are changing optimizer. Instead of gradient descent, we will be using other optimizer. Okay, what is that other optimizer? We will look into it today. Okay, so this is how a neural network looks like. Forward propagation, loss calculation, and backward propagation. So do you see that term optimizer in the red circle below when we go for backward propagation? So that is main thing for getting less loss function or reducing the loss function, getting good accuracy. Okay. So in forward propagation, what do we do? x1 into w1 plus b1, calculating transfer function, applying activation function. And then in step 2, we calculate loss function. And our main aim is to reduce the loss function by going for backward propagation. Okay. So we have seen that in backward propagation, we compute the gradient with respect to what? We compute the gradient with respect to weights. And we've also seen comparing the outputs to desired system outputs, right? So we've also seen that if the output is not as desired, we go for adjusting the weight such that I reduce my loss function. This is what we have seen when we were talking about back propagation. Okay. Now, gradient descent algorithm was the optimization algorithm that we have used earlier for basic machine learning applications. Okay. Now, what do we do in gradient descent? On each iteration, for epochs, for n epochs or for each iteration, we try to update the parameters in the opposite direction such that I reach from a desired point to the global minima. We have seen this diagram, right? So what does this diagram represent? Here I am plotting weights with respect to cost function. I am adjusting my weight such that I reach from a normal point. Okay, I have that initial weight, red dot. Okay, so I want to reach from that initial weight to the global minima point such that my loss function would be reduced. Okay, now this is what we have done in gradient descent, right? We have calculated new weights. Okay, W of new is equal to what? W of old minus learning rate into derivative of the loss functions with respect to weights. What is J? The loss or cost function. Okay, so we were updating the weights by calculating the gradients of loss with respect to weights and multiplying that with what? A parameter called learning rate, which is very small. 0.01 was the small learning rate that we were taking. Okay, so this is what we have discussed so far. Okay, now when we take only weights into consideration, okay, so our map looks something like this. Okay, weight with respect to cost function. But we are not updating just weights. We are also updating bias terms. Okay, so when you take two different parameters, your graph would look something like this. We will have 3D view representation of the parameters getting updated. Okay, when I visualize the counterpart of this, what is counterpart? 2D projection of the 3D graph. Okay, that is the top view of the 3D graph looks something like this. Okay, so I am considering my weights and biases which will affect my cost function here. Okay, on y-axis I put my cost function, on x-axis I am representing my updation of weights and biases. Okay, now let's look into three types of gradient descent. Okay, there are three types of gradient descent algorithms. The first one is called as what? Batch gradient, which we were talking about previously. Okay, the normal gradient descent algorithm is nothing but the batch gradient descent. Okay, apart from that, we also have other two types of gradient descent which are called as stochastic gradient descent and mini batch gradient descent. Okay, what are the three types of gradient descents? Batch, stochastic, and mini batch. Let's look into what each of them stands for. Okay, so what is batch gradient descent? Please look at that. Batch gradient descent is a type of gradient descent which will calculate the error for each example within the training data set. That is what we have done earlier, right? For each example in the given training data set, that is, if suppose I have 100 sample, for each sample we are processing the entire model. Okay, so within the training data set, but only after all training example have been evaluated, the model will get updated. So when will the model get updated with respect to new weights? When all the training samples in the given data set have been processed. Okay, so that is what your batch gradient descent stands for. Okay, so this is how we have seen step by step steeping. Okay, so we will have one initial point, and from one initial point we'll try to reach the global minima. That middle one is nothing but the global minima. The top one is nothing but the initial point that I have taken. So I'll go with step by step decaying, steep decay of the weight such that I'll reach my global minima. Okay, so this is what we do in what? Batch gradient descent. But what is the disadvantage of this? It takes more time. Learning rate or convergence time is more because I have to train all the samples in the data set. Okay, so what are the advantage of this? It has straight trajectory towards the minima. What do you mean by straight trajectory? I am trying to reach from the initial point to the global minima straight. Okay, so that is the advantage, and it is guaranteed to converge in theory to the global minimum. At any cost, I'll try to reach the global minima because I'm traveling straight. Okay, but the disadvantage, as you can see, is it is slow because it has to process what? All the samples. So when does stochastic gradient descent fails? When you have larger data set, when you have more samples. For example, if I have data set with 1 million samples, so training all million samples and updating the model once after all million samples are processed is a tedious task. So we don't prefer batch gradient descent when we work with what? Large data set. Okay, did you get the advantage? What is the advantage of batch gradient? Step by step we'll try to reach the global minima. At any cost we will reach, but as it is a slow process, when I am trying to reach, the convergent rate becomes slow when I am dealing with what? Larger data sets. Okay, so that is the reason we go for the next type of gradient descent, which is called as what? Stochastic gradient descent. So what is happening here? Stochastic gradient descent is a type of gradient descent where the step size is typically much larger. So instead of taking small step size, I am going for what? Larger step size. But what will happen if you go for larger step size? We may cross the global minima. So that is a disadvantage of what? Stochastic gradient descent. Okay, so that is the reason what do? We go for the next type of gradient descent, which is, see, this is stochastic gradient descent. Okay, we may cross the global minima, or when you talk about stochastic gradient or okay, I'll tell you about next one. Okay, did I go back? Yeah, so after stochastic we have what? Mini batch. What do you mean by mini batch is, if suppose I have 1 lakh samples, large data set, I divide that 1 lakh samples into 1,100 mini batches, and I process and update the weights for every 1,000 batches, such that I have more convergence rate, and I can eliminate the disadvantage of stochastic, and I can also eliminate the disadvantage of batch. But there is also problem with this mini batch. Okay, the problem with mini batch is, look at that red curve. The red curve is stochastic or mini batch. Okay, so what you can see is, when I am trying to reach the global minima, I am wasting my time in going in vertical direction rather than horizontal direction. Okay, when I am processing mini batches, I process that samples, all the samples in one mini batch, and I take more time in going in this way. That is, observe that red dashes. Okay, that is mini batch. I am wasting my time going in the vertical direction rather than going into the horizontal direction, because I am processing my samples in mini batches. So one mini batch is completed, and then another mini batch is getting trained. Okay, so this is also another disadvantage of what? Mini batch gradient descent. Okay, so this is batch gradient. What is batch gradients? I steep directly and reach the global minima, whereas when you go for mini batch or stochastic, I am able to reach, okay, I am not crossing my global minima, but the problem here is, I am wasting my time going in vertical direction rather than concentrating on my horizontal direction. Okay, now there should be something that has to be done on this mini batch gradient descent, such that we travel from the initial weight to the global minima, concentrating on moving from the initial weight to Global weight, not in the horizontal direction, but in the vertical direction. Okay. Can you see that black dot inside the red one? Can you see that black lines inside the red one? So what am I trying to do? I am trying to reduce the time that I am taking in traveling the vertical direction. So how does that happen? Okay, that happens by introducing momentum inside the processing. What do? I inside momentum inside the processing. So momentum is another optimization algorithm. Okay, so far we have discussed about one optimization algorithm, which is what? Gradient descent, which has 3 types: batch, stochastic, mini batch. Now in order to overcome the disadvantage, mini batch is the best when you compare to 3, but the problem in mini batch is more concentration in vertical direction, where time taking for processing is more. To reduce that, we introduce momentum inside that. Okay, so when you talk about all the other optimization algorithms that we have, there is one concept, one mathematical concept, okay, which is called as, see, this is the difference between all 3 gradient descents. Okay, batch, mini batch, and stochastic. Okay. So in order to understand what is this momentum, how do I reach from the initial weight to the global minima without concentrating much on vertical, we will first have to understand about this concept, which is called as exponentially weighted moving average. Okay, first let's understand what exponentially weighted moving average, because this is the foundation, mathematical foundation for all the optimization algorithms that we actually see. Okay, so what will happen if we go for good optimization algorithm? The weights would be updated properly. If the weights are updated properly, my loss function would be gradually reduced. If the loss function is gradually reduced, my model will work better. Okay, so my main aim here is to concentrate on updating the weights properly by choosing the correct optimization algorithm. Okay, so we will see what is the best optimization algorithm today in the session. Okay, so first let's understand what is exponential weighted exponential weighted moving average. Okay, now listen, when I am processing the data, okay, so I travel through different data points over time. Right? So when I am traveling through all the data points in time, I may encounter new data points as well. Right? I may encounter new data points. When you look at the graph, those red dots are nothing but the new data points that I get when I travel from 0 to all the data points. The blues are the data points which are already existing. The reds are the data points which are appearing new when I am trying to travel through the entire data set. If suppose I have these 450 students in the class, I may have new students also. Okay, so when I am teaching, whom do I concentrate? I concentrate more on the new students. Why? Because the old students are attending the classes since beginning. They might know ABCs of what I am teaching, but the new students are completely new, so that I concentrate more on them such that they'll understand the session more. Similarly, when we are traveling through the entire data set, we concentrate more on the new data points rather than the old points. So we calculate the average of the new data points which are appearing and give more importance to the new data points than the old data points. Okay, so you'll understand this more when I go deeper. Just look at that expression. What do you see in that expression? I see VT. VT is nothing but the traveling time with respect to the data points. So VT is given by beta. Beta is nothing but a parameter. I'll explain you what is beta later. Okay, like how we are taking learning rate, here we consider one parameter which is called as beta, a very small parameter where the value ranges from 0 to 1. Okay, so I am taking a constant or one parameter called beta and multiplying that with Vt minus 1. So Vt is nothing but the current data point, Vt minus 1 is nothing but the previous average. Okay, Vt is the current average, Vt minus 1 is the previous average, plus 1 minus beta into the current data point. Theta represents the current data point. So what I am trying to do here is, I am trying to calculate the average of the new point, which is Vt, with respect to what? Beta into the previous average with respect to the current data point. Okay, listen. if I am traveling from one place to another place, okay, I'll look into how did the other person perform. If he is well, I'll go to the new data point. Yes or no, I'll check with you. If the answer is correct, I'll know that you are performing properly, then I'll switch on to the next person. The same thing is happening here. VT is the current data point. I'll update my current data point or current average by checking the what? The previous average, which is Vt minus 1 into beta plus 1 minus beta into the current data point, which topic I am teaching. I can't ask you the question from the previous thing, right? So, Vt is nothing but the average of the current point. Vt minus 1 is the average of the previous data point with respect to small parameter, which is called beta, plus 1 minus beta into the current data point. Okay? Now, don't worry. You'll understand it more when I proceed further. Okay, now look at this. What do you see? Initially, the current data point is 0. I start at 0 position. Okay, look at the graph there. Look at the graph. So I'm starting with 0 data point, right? That red line is starting from 0th line. So those blue lines are the existing data points. What are blue lines? Existing data points. What is that red line that I have drawn? I am pointing out to the new data points. Okay. Blue dots are the existing data points, and I am trying to give importance to what? The new data points by drawing a line around it. Okay. Now when I try to calculate V1, V2, V3, what is V1, V2, V3, V4? The average of the current points. That is the red line that I am trying to draw. That is dependent on what? The average of the previous one plus 1 minus beta into the current data point. Okay. So here I say when I am moving from one data point to another data point, my beta value gradually decreases. My beta value gradually decreases. That is, I am giving more importance to the new data points and gradually ignoring my older data points, because I have to concentrate on new data points because they will conquer my entire data set, and that is how I test my model. Okay. Now, look at this. So, how is that red line getting changed depending on beta? When you substitute your beta value in that red line, see, I have taken 3 different beta values. Once I have taken beta to be 0.9, second I have taken beta to be 0.6, third I have taken beta to be 0.95. Which is giving you the best curve? 0.9. No much change, okay, no much oscillations, okay. Are you getting my point? So, beta value can be chosen between 0 to 1, but the ideal beta point that we take when we discuss about momentum is what? 0.9. Just remember, as learning rate is chosen to be 0.01, the beta value by standard we choose it as what? 0.9. Okay. Now, this is what? Starting point that is depicted in blue and the local minimum shown in black. This is what usually happen in stochastic gradient. So what I am trying to do, I am trying to apply this momentum into this such that I am considering weighted averages and I am trying to reduce my vertical line to horizontal line. So how do I do this? In moving the weighted averages, I am ignoring the previous weights. So when I ignore my previous weight, my vertical columns would be gradually reduced to horizontal. Are you getting my point? I am trying to ignore what? I am trying to ignore or decay the previous averages and concentrate on the new data points. By this particular logic, I will try to reduce that vertical line to horizontal line. So what is the main motto here? Reduce that vertical lines to horizontal line by applying what? Exponentially moving weighted average or exponentially weighted moving averages. Is that clear, everybody? Okay. Okay. So this is momentum. So what is momentum? Based on the above example, in order to get use the desired function, we try to add the momentum value to the given batch gradient. Okay. This is what we are trying to do. Okay, we are not trying to process in the vertical direction, but we are trying to process in the horizontal direction by adding what? Momentum. By adding momentum to the gradient descent. By adding momentum to the mini batch gradient descent. Or by adding momentum to the stochastic gradient descent. Okay, this is what happens. Okay, what is the difference between This diagram and this diagram here. The vertical lines are reduced. And I'm concentrating more on my horizontal such that it takes very less time for me to reach from the initial weight to the global minima. Okay. But in this also has some disadvantage. What is the disadvantage? In practice, momentum usually converges much faster than gradient descent. With momentum, there are also fewer risks in using larger learning rates. When you try to reach your global minima, the learning rate gradually gets affected in your momentum. As it gets near, the larger learning rate will have effect on what? The global minima reaching this. So that is the reason we go for next optimization algorithm, which is called as what? ADA-grad. So what is the disadvantage of momentum? As the learning rate is increased, it will have effect on reaching the global minima at the last points. Okay. So we go for the next optimization algorithm, which is called as what? ADA-grad. Okay. What does ADA-grad stands for? Adaptive gradient descent algorithm. Now read that and tell me what am I trying to do here? What is the change that I am making here? ADA-grad is another optimizer with the motivation to adapt what? The problem with momentum was the learning rate getting, because of the learning rate, my steep getting affected. So in order to overcome the disadvantage of momentum, we'll go for this next optimizer, which is called as what? ADA-grad, which is nothing but adaptive gradient. That is, we adapt the learning rate to compute what? Gradient descent. Okay. So, yeah. So how do we do that? By calculating the square root of the weights. By calculating the what? Square roots of the weights that we are calculating. But still, even this has a problem. What is the problem? Read the second paragraph. The learning rate again constantly decays. Even if you go for square also, squaring of the parameters also, the learning rate still get decays when you go for increasing number of iterations. That is, ADA-grad will also work when you work with smaller data set. When you go for larger data sets and when you try to increase the number of iteration, even this will get affected. Hence, we go, see, look at that. Look at that. Initially, my horizontal line is very broad. But as I reach to my global minima, again I am getting curves and again I am getting time taking for reaching the global minima is again getting affected. So this is the problem of what? ADA-grad. Okay. Hence we go for the next algorithm, which is called as what? RMS prop. So instead of just squaring, I'll go for what? Root mean square. I go for what? Root mean square. So what is that? RMS prop. Root mean square propagation. Okay. Now, again, this also individually cannot be used because this will also have adverse effect on decaying the learning rate. Okay. So we have seen momentum, we have seen ADA-grad, we have seen momentum has the problem with the learning rate. So we have gone for adaptive learning rate. Even that has problem when we go for larger sets. We have gone for RMS prop also. So the final or the best algorithm is decided to be ADAM, which is the next optimizer. So ADAM is combination of momentum and RMS prop. What is ADAM? The combination of what? Momentum and RMS prop. From momentum, what are we taking? Reducing the vertical lines. And from RMS prop, we are squaring it such that we try to slowly decay the learning rate decaying problem. Reduce the learning rate decaying problem. So ADAM is the best algorithm for neural network designing when you go for backward propagation. Gradient descent is the first basic optimization algorithm. After that we have momentum, ADA-grad, RMS prop. But the conclusion of all this, okay, or the optimized algorithm of all the optimization algorithm is what? ADAM, which is combination of what? which is combination of momentum plus RMS prop. Okay. So, in our exercise today, we will be working on with what? Adam optimizer. Is that clear, everybody? So we have to work on with what? Adam optimizer. So let's study Adam optimizer in detail with respect to equations. Okay. So Adam is the most famous optimization algorithm in deep learning. At a high level, Adam combines what? Adam combines momentum and RMS prop. Okay. So to achieve it, we will keep track of exponentially moving averages for computing gradients and squared gradients. When I talk about momentum, we'll keep track of what? Exponentially moving averages. When I talk about RMS prop, we consider squared gradients. So in short, we have these two formulas, which is VT and ST. What is VT? VT is for momentum, ST is for RMS propagation. Okay. Now look at VT very clearly. What is VT? VT is equal to beta 1 into VT minus 1, the previous average, plus 1 minus beta into derivative of weight. That is the current data point. Are you all clear with this? So what is VT? For momentum, average, moving weight average for momentum, which will reduce those vertical lines into horizontal lines. Okay. So what is ST? RMS prop calculation, which will reduce the problem of learning rate decaying. Okay. So we will combine these two equations and calculate our new weights, which is WT is equal to WT minus 1. Old weight is equal. See, what was gradient descent? Old weight is equal to new weight minus alpha into derivative of J with respect to weights. So here for Adam, we have new weight is equal to old weight minus VT by square root of ST. What is VT? Momentum. What is ST? RMS prop. This is how we update new weight in Adam. Is that clear, everybody? So new weight in Adam is WT, which is calculated with respect to what? VT and ST, where VT stands for momentum, which will reduce the vertical line. ST stands for RMS prop, which will try to reduce the learning rate decaying problem. So combining this, we will have that new weight updated equation. So in order to write the code, I'll give you more clear understanding. Now this is how your Adam works. This is how your Adam works. So do you see any issue with this now? You're trying to reach from the initial point to the global minima without concentrating much on the vertical lines, and we don't have much decaying towards the end when we are trying to reach the global minima. So this is how we use Adam optimizer. This is how we try to reach the global minima using which algorithm? Adam. Is that clear, everybody? So today would be I know this is complicated, but this is more important concept in deep learning. Okay. So I thought of discussing this because you have vacations now. So you can concentrate more on how does Adam or how does a different optimization algorithm will affect the model performance during your break time. Okay. Now listen. Okay. So what is Adam? Adam is combination of what? Momentum and RMS prop. Look at the equations for momentum. Okay. So I want to calculate V with respect to weights, V with respect to biases. Look at this. When we were looking gradient descent, we were calculating W1, W2, B1, B2. What is this W1, W2, B1, B2? Weights and biases, right? So here also we calculate VW2, VB2, VW1, VB1. Similarly, SW2, SB2, SW1, SB1. That is what you're supposed to write in your coding. How do you initialize Adam optimizer variables? VW2, VB2, VW1, VB1, SW2, SB2, SW1, SB1. This is step 1. Okay. So you have to initialize weights and biases of Adam by taking VW2, VB2, VW1, VB1, SW2, SB2, SW1 and SB1. Okay. So that is a formula which I have already told you. Beta into VT minus 1 plus 1 minus beta into theta. Okay, so this is how we calculate and update your Adam parameter. Okay, in Adam, W is equal to what? W old is equal to W new is equal to W old minus learning rate into VDW by square root of SDW plus epsilon. Okay, epsilon value is usually taken as 10 power minus 8. Okay, now in the coding what we do is, now let's get back to the programming. So we have to initialize our Adam optimizer, in which I am passing parameter n underscore x, n underscore h, n underscore y. You can take the old parameter variables. This is x, input state, hidden state, output state. N underscore x is what? Input state. N underscore h is what? Hidden state. N underscore y is what? Okay, here we have to return what? VW1, VB1, VW2, VB2, and so on. And we have seen the formulas for that. What is VW1 and all that. Okay, so after you return this, we have given you the explanation clearly in the notebooks. After we do this, we have to update the parameters. Now look at the updating parameters. What am I taking? I am taking W1, B1, W2, B2. These are old weights, old biases. DW1, DB1, DW2, DB2 are the derivatives. And here I am calculating what? VB2, VW2, VB2, VW1, VB1, SW2, SB1. Okay, along with that, I go for learning rate. I take beta value. Beta 1 is for momentum, beta 2 is for RMS prop. Okay, and then we also take epsilon. So these are the two changes in the code that we have to make. Is that clear, everybody? First, we have to design what? First of all, we have to define initializing Adam, that is VW1 to SW1 and all that. And then we have to update parameters. The basic weights, derivative of weights, VW of weights, SW of weights, learning rate, beta 1, beta 2, epsilon. Is that clear, everybody? So this is how your optimization algorithm works. And what is the best algorithm that we have chosen out of all the conclusions? Adam. Adam is a combination of what? Momentum and ADA grad. So that vertical lines would be reduced and the learning decay rate would be reduced. Okay. So what we have done in the exercise is to reduce your work. We have given the code for the basic steps, that is reading the data set, calling the importing libraries and all. Only where you are required to code is open up. Please work on that and try to complete the exercise. So we'll see to what extent we can do. We'll on the exercises, please start working on that. Same regression algorithm, same insurance data set. What is the change here? Instead of using gradient descent, we are using what? Adam optimizer. Clear, everybody? A2 is also on. Even you just have to train, test, split the data. Okay. In A2, perform standard scaling. In A2, you have to initialize the parameters and do standard scalar. See, we've already completed so many sessions. We have completed 2 models also. You have to be very fast now. Test case 1 is there in A1 where it is train, test, splitting. Test case 2 in A2 which is used for checking, updating the parameters, initializing the parameters.